So far in the 10 lecture module of numerical problems in process metallurgy, I have tried to solve many problems from different area of process metallurgy, but I realized at the end of the 10th lecture that I have really omitted an important section and an important topic which bears considerable importance in mineral engineering as well as in process metallurgy. So, I want to complete that exercise today and complete the 10 or the 11 lecture module, so that this can really assist you or give you necessary guidelines to solve various kinds of problems that you will encounter. Now, so today's lecture is going to be extensively devoted to mineral processing, and I would like to address two different kinds of problems from two different arena. Number one is classification. What is classification? Sorting according to particle size, and which finds extensive application in mineral processing, particularly in gravity separation and other classifications which involve settling of particles in different media. So, I will talk about problems of interest in classical classifications, and also towards the end of the lecture I will discuss how to solve for power consumption in the crushing and grinding circuits, which are also very, very important. So, we continue with our discussion on problems, numerical problems in numerical problems in process metallurgy, and I will give you the basic theory extremely quickly, so that we can really solve the problems, because it is important to revise the necessary fundamentals. Just posing the problem is not enough for us. So, and from two different area, one is classification and the other is power consumption in crushing and grinding. Circuits, simple problems, okay, and the lecture is devoted exclusively to the area of mineral processing. So, which will give you a complete coverage of problems from iron making, steel making, transport phenomena, as well as mineral engineering. Now, as far as classification is concerned, many of you may have heard the term, for example, free settling and hindered settling, okay, and these are taught to you in your third year or second year mineral engineering course with regard to separation of particles or classification according to sizes. Now, most of the time these classification theories or free settling theories are derived on the basis of laws of settling, as well as laws of settling which are derived essentially from force balance equation, and in this context the most elementary and the simplified one is the Stokes law of settling, and Stokes law also most of you have come across. So, basically the Stokes law, as you all know, it talks about settling or rising of a spherical particle, okay. So, suppose the fluid, most of the time I would say that the particle could be settling down, the fluid could be generally stationary. That is what is the scenario, and it talks about that if you have same material, two different particles, bigger particle will settle faster, smaller particle will settle later. In the same fluid, if you have material A and material B, and you say that the sizes are more or less equal, okay, then we will say if particle density of B is greater than A, then the particle B is going to settle down faster. And these are basically in the context of stagnant fluid derived from Stokes law, and on the basis of Stokes law, and the Stokes law itself is derived on the basis of Newton's second law of motion, that is when a particle settles or rises with a constant velocity, which is termed as terminal rise or terminal settling velocity, there is no net force acting on the particle. So, the summation of forces is equal to 0, and if you now consider the various forces, that summation of forces means what are the kinds of forces, you find that there are 3 different forces: gravity force, the buoyancy force and the drag force on the particle. So, these 3 different forces are in balance. One can show that the gravity force is nothing but the weight of the particle, which is equal to 4 by 3 pi r p cube into rho p multiplied by g. Mass into acceleration, mg is the weight. Buoyancy is the mass of the displaced fluid. So, therefore, this is going to be rho fluid 4/3 pi r p cube into g, that is what it is, mass of the displaced fluid. So, therefore, the density, volume of the solid comes into the picture, but the density becomes the density of the fluid, and then it becomes the mass of the displaced fluid, because whatever is the volume of the particle is the same amount of volume which is going to be displaced, and hence once you multiply it by the fluid density, you get the mass of the displaced fluid multiplied by g, and you get the weight of the displaced fluid. So, that is equal to weight is force, and similarly the drag force from the classical theory of fluid mechanics comes out to be 6 pi mu r p into uw u infinity, where u infinity represents the terminal settling velocity. So, if you now club these things up together, okay, then you will find that u infinity is given in terms of 18 mu g dp square into rho particle minus rho fluid. The Stokes terminal settling velocity of the particle is dictated by this expression, which is derived on the basis of the force balance, and this is the expression that we call as the Stokes law of settling. If you change the sign rho f minus rho p, then you get the same law, but it is going to be now, instead of settling, it is going to be the rising velocity itself. So, therefore, we can say now this is the basis on which most of the classification calculations are done, and therefore, you can say that the free settling ratio is determined now, for example, in which dp is essentially 2 times rp, that is what it is, twice the radius of the particle. Now, based on this, you can say that if you have 2 different particles A and B, where you have radius of the particle as r a and radius of the particle as r b, you have density of the particle as rho a and density of the particle as rho b, then if we say that both these particles, under what condition this is going to be satisfied, then on the basis of Stokes law, we should be able to find out that what is the corresponding relationship which will fulfill this requirement. And so, these are the 2 solids, one solid is A, denoted by A, other is denoted by B. This is the radii of the 2 solids, these are the density of the 2 fluids, and these are, for example, settling in a medium which has a density of rho fluid. And I want that, let that be R A and R B, but I want that under what condition you tell me that the 2 particles are going to be settling at the same rate and same velocity, and then I say on the basis of Stokes law, we will find out that R A by R B is equal to rho particle, it is settling, okay. So, rho particle is greater than, so rho particle A, this is A and this is rho fluid, and rho particle B, or I can say just rho A and rho B, that is better, I think. And this ratio is termed called the free settling ratio. The free settling ratio under the condition when Stokes law is valid. And under what condition Stokes law is valid? We know that the Reynolds number of particle is to be much greatly smaller than 1. This tells us that the particle size has to be extremely small. This tells us that the velocity, okay, also is to be extremely small. And therefore, that is why I said Reynolds number, which is rho times rho fluid times mu, and then we say u infinity, and then if you say diameter of the particle. So, if this term u infinity is small, dp is small, it turns out that the Reynolds number is obviously going to be extremely small quantity, and Stokes law is valid for you to remember under the condition that when Reynolds number is equal to is almost 0 or much less than 1. If you find out that Reynolds number is not 1, in that case what we do? We apply Newton's law, and in this Newton's law we say that the power is no more now half, but it is 1. Okay? And there is another term which we call as a hindered settling ratio. So, when the exponent, if you generally say that this is n, then we will say n is equal to half is our Stokes law. N is equal to 1, n is equal to 1 is Newton's regime. That means the particle may be little bit of bigger, the particle may be settling with a little bit higher velocity, and therefore, and there is another term as opposed to the free settling ratio is the hindered settling ratio, HSR. FSR is free settling ratio, HSR is hindered settling ratio. The only difference is here is that the hindered settling ratio is calculated on the basis of rho double prime. And what is that rho double prime? That rho double prime is called the pulp density. Okay? And how is the pulp density determined? It determines on the basis of the solid, because there may be, when the part free settling means, you can imagine free settling means pulp density is small, particles are not colliding with each other, that is what it is called, the particle is freely moving. Hindered settling means there are so many particles in the surroundings that as the particle is settling, it is colliding with left one, it is colliding with right one, and therefore its settling is hindered, and as a result of which the term we coined is the hindered settling ratio. So, this is the pulp density, and this pulp density is typically calculated on the basis of solid and liquid volume fractions or weight fractions in the system based on the continuum approximation. So, rho double prime is basically a quantity which is rho mix, solid liquid mixture. So, and this is to be calculated, you remember, always from the continuum approximation, or we do it conventionally from continuous approximation. So, we say that weight percent solid multiplied by rho solid plus weight percent liquid multiplied by rho liquid. For example, we will solve a problem, and that suppose we have a mixture of galena and quartz, and the fine particles of galena and quartz we dump, and suppose we are interested in finding out that that how the galena particle settles here. So, these quartz particles may occupy about 40% of the domain by weight. So, therefore, what is going to happen is that it is going to be the medium is not purely fluid, but the medium contains through which the galena particle is settling contains already suspended solids. So, its density is going to be much higher than the density of the fluid, because the solid's density is greater than that of the liquid. So, in the context of a galena quartz mixture, if I tell you that the quartz is in suspension, in that case you can imagine that the galena particle settling would be colliding. It is not a pure scenario that is a clear water. No, there are suspended particles of quartz. So, as a result of which what happens is we have to consider the effective density or the solid liquid mixture density to find out that in that through that mixture how much time Galena particle would take to settle down into the system. So, if you have for example 40% by weightage, if it is given, of course, you have to know the loading, that is called the loading ratio, solid loading ratio in the system. So, if you have 40%, so I would say wet percentage solid is 0.4, wet percentage liquid therefore is 0.6 multiplied by rho s, 0.4 into rho s plus 0.6 into rho liquid, and that is the density that is to be used, and that is basically what is the rho double prime which is to be calculated in the context of Hindered settling ratio. Now, with this background, let us quickly formulate two problems in this area and then explain you the solution. So, the first problem that I want to pose is, let us see that a system is there, a vessel is there, the vessel contains non-metallic inclusions, and non-metallic inclusions are lighter than steel. So, this is steel and there is a non-metallic inclusion here, very small size. Let us say that the diameter of the non-metallic inclusion is 100 micrometer. It is a very small particle. So, we understand that as per our hypothesis, Stokes law is going to be applicable in this regime, and we want to find out that rho of NMI is greater than rho of steel. Sorry, it is other way around, much. This could be about, if it is aluminum inclusion, this could be about 3000. On the other hand, if it is steel, then the bulk liquid density could be about 7200 or so on. So, therefore, it is understood that this will be rising in the system. Our interest as far as process metallurgy is concerned, we want to examine that is it really possible to float out such size particles in the system or not. So, a limiting calculation can be done based on Stokes law. So, the question that I pose is, examine the possibility of flotation of a 100 micron size particle over a distance of, say, what did I say, this is 3 meter suppose. So, this distance let us take, this is total is 3 meter, that is the typical bath depth of a ladle. So, from the mid bath depth level, so it is 1.5 meter. Suppose an inclusion hypothetical is there, mid bath level is present, and I want to find out that if the diameter is 100 micron, then what should be the time taken to float out. So, because this is small particle, so I can calculate the terminal rise velocity, and the terminal rise velocity is 18 mu, and rho steel is given as 7200 kg per meter cube, rho particle is given non-metallic inclusion 2740 mid kg per meter cube, everything I am trying to put in SI unit, and viscosity of the fluid is given to be 0.007 kg per meter dot second. So, U infinity is equal to now G dp square, diameter of the particle, multiplied by rho p, rho fluid, it is settling, minus rho particle. That is, so we will substitute the value of 9.81, diameter is 100 micron, we will put in meter. So, meter, we say micrometer, so this is 10 to the power minus 6 raised to the power 2, and then this is it is 7 to 200 minus 2740, and this is divided by 18 into 0.007. That is what it is. And this U infinity now, make a habit of writing the unit also along with the, you will never do a mistake. Most of the time you tend to do a problem by mixing the units, that is not desirable. Convert everything to SI unit and then solve, and adjacent to the parameter you also write down the units in which the value is going to come out, so that you can never get confused. And if you put this value here and do the calculations, this is going to come out to be 3.5 into 10 to the power minus 3 meters per second, which means 3.5 millimeter per second, and this is a constant velocity as we know by the definition. So, therefore, we can say that the time taken to rise the particle is going to be 1.5 meter divided by 3.5 into 10 to the power minus 3, and this is going to be in seconds, and this value comes out to be something like 428 seconds, or roughly about 7 minutes. So, we can draw a subjective conclusion that possibly based on this calculation I can possibly make a deduction that sir looks like such an inclusion may float because 7 minutes, but if you are talking about 20 microns or 30 microns inclusions, possibly they will never come out of the system. That is a conclusion that one can make from this particular scenario. Okay. Now, let us go to the other problem. This one I would like to do it with regard to free settling ratios, for example, and the hindered settling ratio. Okay. So, I have to, because I am posing the problems, not writing them, and I have to use some numerical values. So, I have to take help from my notes, so that I can plug in the right values and do not do the mistakes. So, and I think those of you who are interested in solving problems, because unless you solve problems you do not get numbers, and unless you get numbers you do not see. Merely saying he is taller than I am is not enough, but the moment you say that he is 6 feet 10 inches and I am 4 feet 9 inches, it gives you an idea that, oh my God, there is substantial difference between the two. So, that is what the number helps you to get a clear picture of the actual scenario. So, free settling problem on free settling. Free settling ratio. So, what is the problem? Calculate the free settling ratio of quartz and galena in water. So, suppose a big water mass is there in the vessel, it is a free settling ratio. So, it contains a fluid here, I will tell you what is the fluid. Then we put in some galena particle, you know what is galena, and we have quartz particles also which are intermixed, okay? And not too large an amount of the volume of the particle added is not comparable to the volume of the fluid. So, as a result of which the free settling approximation applies. But if the volume of the particle added is comparable or a sizable proportion of the volume of the fluid, in that case the free settling is not going to work out. Free settling means, this gives you an idea possibly that there are 50 galena particles and 100 quartz particles. This is the kind of a scenario we are talking, and that is when the free settling ratio expressions are applicable. So, calculate the free settling ratio. Okay. Settling in water. So, fluid is water. So, water has a density of 1000 kg per meter cube, and the density of galena is given as 7500 kg per meter cube, and density of quartz is given to be 2650 kg per meter cube. And free settling ratio is to be calculated on the basis of n is equal to half, that is the Stokes law is applicable. So, I would say R galena by R quartz is equal to rho galena minus rho water, and rho quartz minus rho water raised to the power half, and this exponent half has come because I am applying the Stokes law, which is valid for free settling ratios. And if I now do plug in this ratio, then I get that this is equal to 2650 minus 1000, okay, and this is equal to 7500 minus 1000 raised to the power half, and this value comes out to be something like 2.08. What does this indicate? This indicates that the Galena particle size will be 2 times the quartz particle size, which will have the same settling ratio. So, therefore, you can imagine that these particles, if I draw it, they are on the basis of this, they are coming down, okay. There are 2 different particles. So, these 2 particles are coming down at the same speed. So, the size of the Galena particle, and so this is say quartz and this is Galena. So, the Galena particle as it is shown here, so it is other way, sorry, this comes out to be 2, I missed that value, okay. So, this is that is what, so this is roughly 1 by 2, so therefore, this is 0.5. This value is has to be less than 1, this is denominator is much stronger than the numerator. So, the value comes out to be, so which essentially means that the Galena particle, okay, is only half the size of the, so it is other way around, okay. So, I will say that this is Galena particle is smaller, the quartz particle is larger, and they have the same velocity. So, you can now imagine that if I wait for half an hour and allow this particle to settle, then I will see while the finer particle of Galena has settled, coarser particle of quartz, and then I can separate them out very easily after drying the mixture itself. So, there is going to be huge gradation in terms of the particle sizes. The particles after half an hour, if I collect the particles from here, and I will see I will have on Galena particles much smaller than the size. So, I can dry them and use a mesh and just screen them, while the big particles can be separated and the smaller particles can be isolated, and that is the way it is basically done in the system. So, this gives us an idea that we know that Galena part being heavier will settle faster, but this expression gives us that at what rate it is going to settle, and that tells us that the size differences having the 2, it is not proportional, directly proportional to the density difference, it is proportional to density difference raised to the power half. So, therefore, we can say that the Galena particle which is going to be settling with the same speed as the quartz particle, actually half of the size of the quartz particle. So, after any time you consider that it is a finer particle of Galena will be settling relative to the coarser quartz particle. Now, let us pose this problem, convert the same problem to what is known as the Hindered settling ratio. So, therefore, if we want to do it in Hindered settling ratio, we cannot use this. So, we have to use rho double prime, which is the pulp density. So, now one thing is given, it is the same problem, the pulp contains 40 weight percentage of quartz. So, the same problem to be applied considering the Hindered settling free settling ratio, Hindered settling ratio is to be calculated. So, 40% quartz is there loading and 60% is water, 60% is water. And as I said that, so what we expect 100% water if it has a density of 1000 kg per meter cube, and if now we have quartz density of quartz is substantially larger than that of water. So, with 40% quartz suspended in water, what will be the effective mixture density? Less than 1000 or more than 1000? It is going to be substantially more than 1000, because quartz is much heavier than that in water. So, 40% of quartz which has replaced water from the system, okay, will give rise to an increase, and according to, so rho double prime is equal to rho mixture will come out to be 0.4 into 2650 plus 0.6 multiplied by 1000, and that gives us a density of, I think, 1660 kg per meter cube. Yes. And now this, if you now, so we have to remember this, that once we solve a hindered settling problem, we have to use the pulp density, and to estimate the pulp density, this continuum formulation needs to be applied. Okay? That is the only tricks in the whole system calculation. So, therefore, I can say now that, look, this equation, I will say that this is now, I will replace it by rho double prime, and I will replace it by rho double prime. Now, I want to make one simple comment. In hindered settling, okay, most of the time what happened is this exponent half is not applicable. Okay. So, the exponent n is, that is the typical exponent that one uses in hindered settling. So, this is to be specified to you. Okay. If you are given to solve and it says that use a value of n is equal to 0.75 or 0.8, you must understand that he is talking about the exponent on the density differential ratio term. Okay. Let us solve, because we have solved the value with regard to half in the other problem, free settling ratio. So, in this case, let us solve, let us consider that I give you that n is equal to half, and therefore, we can see that R galena by R quartz is equal to, now this is rho quartz 2650 minus 1660, okay, and this is density is galena is 7500 minus 1660, and because I have specified the value of n is equal to half, so therefore, I can say that I can write this, but you can put 0.75, 0.1. The issue is that the value of the n must be given to you to solve the problem, and if you do this, the value will come out to be 0.25. And what does this indicate? Now, the size ranges have even become more stronger. What does it indicate? That quartz is now facing more problem actually to settle. I mean, you can imagine that if you have, I tried to give, when I was teaching this non-ferrous metallurgy course, to explain the hindered settling, I gave this example, and the boys laughed, that suppose you have a small door, and through which people are going in, and you imagine a stout person comes in and there are chota mota 4 or 5 guys, so he will push them aside and get into the hall. Okay? It is the same phenomena which is happening. Lead galena particles are mightier, the density is there, mass is there, so it is forcing it through the medium, and as a result of which, now even in the case of hindered settling, much finer particles are going to be settling. So, the conclusion is that, what in reality, what we will see, because real phenomena corresponds closer to the hindered settling, because we have to use a large tonnage of material. Okay? So, free settling will rarely be obtained. So, whatever values we can obtain on the basis of free settling ratio, we can expect that the scenario is actually going to be better than that in actual reality, because the lighter particles are going to be experiencing more amount of resistance while they settle to the bottom of the vessel during classification process. Now, having said this, I will discuss the last point, which I said, to conclude formally my discussion on the numerical problems. So, this is, I will give you very quickly the background of crushing and grinding, and many of you may have studied the laws of crushing, for example, is a very important, and we want to quantify crushing because of the simple fact that with the reduction of sizes, the size reduction is accompanied by a huge power consumption. So, crushing and grinding is energetically intense process. So, there is considerable interest to know that if I grind up to this level or if I crush up to this size, what will be the power consumed per ton of material. So, classically there has been considerable interest, and there are many laws which have been advocated to quantify this energy business in the context of crushing and grinding. And the most, you may have learned that there are three popular laws: Stokes law, Rittinger's law, and Bond's law. These are, as far as undergraduate. And the general expression, the energy consumption, is given in terms of an expression where x represents the particle size, n is a power, n is an index, and this is the general expression for and there are that when you crush material, there are surfaces, additional surfaces which are created, and it is based on that surface energy considerations people have worked out this kind of a formulation. So, we are not going to the details of it, but this can be considered to be a general expression for all these three laws. And we say that when we this value n can take really a value of 1, 2 and 1.5. That is the values which are prescribed. When you put n is equal to 1, what you get is the Stokes law. So, I will say n is equal to 1 is Stokes law, n is equal to 2 is Rittinger's law, and n is equal to 1.5 is the Bond's law. That is what comes out, and you can integrate very easily. So, if you just put n is equal to 1, so dx differential x with respect to x to the power 1, so it is going to be in terms of log. Similarly, if you put 1.5, you will see that the integral will come out to be, you are integrating it, the energy consumed from an initial size to final size, the x is to be integrated. So, x initial to x final, if that is your target. These are the limits of integration, and if you do integration by putting x to the power 1.5, n is equal to 1.5, when you get Bond's law, you will see the integration will result square 1 by square root of particle size, final particle size, minus 1 by square root of initial particle size. So, it is a 10th class or 8th class exercise. You should be able to derive, this is the differential form of the equation, and the integral form of the equation also you will be able to derive, and you have E is equal to some constant k given in terms of 1 by square root of particle size. So, I will say x of final minus 1 by, this is x of, where k is a constant, which depends on the kinds of machine that you use, properties of the ore, all these kinds of. So, for example, if you take galena, some ores are soft, some particles are hard. So, therefore, even though you may have similar size reduction, the power consumption is not going to be same, because there is a constant term here, and this constant depends on the crushing machine, this constant depends on the nature of the ore or the material to be crushed, and so on and so forth. And that tells us that even for similar size reductions, different particle or particle having different characteristics undergoing crushing in different machines will yield different. Based on this, then these constants have been defined. For example, in Bond's law, it is said that this constant, which is called as is converted into a Bond's work index, which is defined as the power required per ton of material crushed by taking by crushing material where 80% of the material passes through a 100 micrometer screen. So, you have taken a very big size. So, the moment you take very big size, this term becomes equal to 0. Okay? Initial size is infinity, and then the final product you are saying that this is going to be passing. My requirement is that it should pass through 100 micron size screen, 80% of it should pass. And in that case, if you experimentally determine E, you should be able to find out that what is the K parameter for that ore for that particular machine. So, it is based on that these parameters are determined, and this equation cast in a different way is given in terms of, for example, the power divided by per unit mass is equal to Wi and 0.312 into 1 divided by particle size final minus 1 divided by particle size initial, where now you must understand that this Wi is related to K, this is called the work index. Okay. And where from this 0.312 has come? This 0.312 has come from the conversion of microns to centimeter, microns to millimeter. So, therefore, you have to put in this expression x in millimeter. So, you can imagine it is when you convert micrometer to millimeter, a 10 to the power minus 3 factor will come, square root of 10 to the power minus 3 will come, and then the inverse of that will come out to be 312. So, you can clearly verify it. So, therefore, okay, and this is a material, as I said, that K can be determined a function of machine characteristics as well as the ore, and this is called the Bond's work index, which is typically given. And as I said, Bond's works index is given in terms of the energy required, okay, the power required for per ton of material. So, it is if it is power, then we say it is kilowatt or watt, and it is mass flow rate. So, it is going to be kg per hour or kg per day, whatever it may be. So, this can be, this is actually basically kilowatt hour per ton. You can see the unit of this. This is P is power, kilowatt or watt. This is feed rate, which is tons per day or tons per hour. So, therefore, this could be kilowatt hour per ton, energy consumption per ton of material. And Bond's works index basically tells you that if you it is equal to the power consumed per ton of material once you take a very large size particle, crush it such that 80% of it passes through the 100 micrometer screen, and then you will see Wi comes out to be is equal to this. So, this quantity Bond's work index will be given to you, okay, and it will be given to you in terms of the unit I have just now expressed. Now, having said this much, you can read this in any of the I have given you in nutshell, because I cannot go on discussing, but the whole crux of the problem that is that I have discussed here. Most important part is that in this equation that I have written here is x is to be substituted not in micron but in millimeter, because micron to millimeter conversion has been taken care of in this. And from here to here, how you arrive, it is a simple exercise that you yourself would be able to find out. Okay. So, let us say that we want to pose a problem using, we want to calculate the energy consumption in a crushing circuit based on Bond's law. So, we are given that a material is crushed, okay, and now it is given that the work index Wi is given. You can see, you can imagine that what is the unit. This is dimensionless, okay. This is millimeter to the power half. So, therefore, this is kilowatt hour per ton into millimeter raised to the power half, that is the unit of work index. Okay. So, work index of the material is given to be 12.75 kilowatt hour per ton into millimeter raised to the power half. The feed rate is given to be 100 TPD, tons per day, and we are given that feed is such that 80% of the feed passes through 2-inch screen and product 80% of the product passes through 1/8 inch. This is just a redundant exercise. I could have directly given you the values in millimeter. Okay? Just to, I deliberately put the value here because I wanted it to convert it and put it into this equation in millimeter so that you never forget. Do not substitute the value. So, 2 inch is basically in terms of millimeter, I would say that this is 1 inch is equal to 2.54 centimeter. So, this is 5.08 millimeter and this is 3.175 millimeter after conversion. So, I have obtained the value of XF, I have obtained the value of WI is given to me, m dot is given to me. So, the power can be calculated, one equation, one unknown, piece of cake. And if you substitute the value now, the power in kilowatt hour, okay, in kilowatt, the hour will not come into the picture because feed rate is tons per day. So, you have to convert it tons per hour. Okay. So, therefore, we will say this is going to be is equal to this is feed is there is no conversion here, tons per hour, that is the correction, okay, tons per hour. Otherwise, I have to put in a factor of 24 hours and day conversion. So, I have made my life simple by putting. So, I will multiply this by 100, I will multiply this by 3.16, I will multiply this by the work index 12.74 and I will say that this is equal to 1 divided by 3.176 minus 1 divided by 5.08. So, you can calculate the value, okay, by using a calculator, and for the given problem this will come out to be something like 169.6 kilowatt. So, this is typically the kind of problem that you can expect either in an exam like GATE or in your classroom examination from mineral engineering, and you should be able to these are very simple, there is no reason why you should mug it up, it should come out very spontaneously. One or two pulp density issue, and similarly the particle size in the bonds equation as in millimeter, not in inch or not in other units. These are the few things which you have to remember and just plug in the values and you should be able to calculate. So, I think this holistically closes our section on problem solving. So, I think these 11 lectures you should find quite useful, and give you necessary guidance while solving related problems, because I cannot solve each and every problem in this limited time, but I have nevertheless given you some directions which will allow you to think and tackle problems which will be posed to you from time to time. Okay, thank you.